let's also draw some examples of the electric field lines. We had already drawn the dipole. Now, what about the planar charge distribution? How does the electric field lines look like? Let's just imagine that this is our plane. This is our surface charge. I'm just looking from the side. So how will the electric field lines look like? How? I mean, like this?
Is it infinite?
It's infinite. It's infinite.
Then they just go out.
Just readily out. Now we had already shown that the electric field line, the magnitude is sigma over 2 epsilon 0. So we know that the magnitude doesn't change, but if the magnitude doesn't change, it just means that the density of the electric field lines should not change from point to point. We also know that the electric field lines always point away. We had derived that it points away from the plane. So these will be the electric field lines. Their density is always the same. Now, electric field lines, don't treat them as a tool to make quite precise calculations or computations. It's just qualitatively, how does the electric field look like? It should give you an idea about how they behave in different points, but not a precise tool for calculation. Now, any questions on electric field lines?
They are not intersect each other's, but I'm thinking if there is a magnetic field.
There is no magnetic field yet. We are looking in electrostatics. The only thing we have is an electric field. Okay, let's look at some of the consequences. Let me draw again. Go back to the dipole. Plus Q, minus Q. We said that these were the electric field lines, and let's just agree on the convention that from a plus Q charge, I will draw 8 electric field lines for every plus Q charge or minus Q charge. So I should have 8 electric field lines from the plus Q, 3, 4, 5, 6, 7, 8. No. Plus Q, minus Q. Let me just draw 4. So these will be the electric field. Let me draw 4 more. And these are the directions of the electric field lines. Do you agree? Let me just now imagine some spheres. Here I have a sphere. I will count the number of electric field lines that pass through the sphere. If an electric field line goes from inside to the outside, I will just count plus 1. If an electric field line goes from outside to inside the sphere, I will count as minus 1. Agreed? Now, what is the number of electric field lines passing through this sphere? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. All of them are going from inside to outside. Let me just put it over here, just small number 8. Let us consider this one. How many electric field lines 1, 2, 3, 4, 5, 6, 7, 8 of them, but they're all going inside. If they are going inside, I will just count them as -1. So there's -8. Let me draw this one. Let's count. Let's see. There, I didn't draw any electric field line. Here, this is +1, +2, -1, it gives +1, and -1, that is 0. What about this one? Again 0. -1, another -1, -2, +1, -1, plus another +1, 0. Now remember our convention. We agreed that for a +q charge or a -q charge, I will draw 8 electric field lines. That was our convention. Now let's look at this sphere first. We said there are 8 lines passing through it. What is the total charge inside? +1. For +q, we said 8 lines. In this one, what is the total charge inside? -1 and -8 lines. Well, minus just means they are going inside. What is the total charge in this sphere? 0. Well, in this sphere I have this +q charge, this -q charge, so it is 0. And the total number of field lines passing through it, the net number is 0. And similarly in this one, there is no charge inside. And the total number of electric field lines passing through it, well, there are some electric field lines passing by, but they are entering and leaving, so the net number is 0. So essentially, if you count the number of field lines, it gives you an idea of what is the total charge inside. It is the shape of this sphere is not important, because if I, for example, consider this sphere around this one, if you just count them, you will again see that it is 8. Now the reason is basically just we said that the electric field lines cannot terminate or cannot start from empty space. They should start from some charge and they should end by some charge. Well, since there is no charge inside the sphere, whatever electric field line comes in should leave out. It cannot end in this. There is nothing to end here. Now, if we imagine this larger one, it does have some charges, plus charge or minus charge, but if there is some electric field line coming very far away, it can end in one of them, but then there should be another one leaving from that charge. Like this one over here, there is one leaving and there is one coming in. This is the basis of the Gauss law. Now we will make it more formal. It just we can express the Gauss law as the net number of electric field lines passing through a closed surface is proportional to the total charge inside. Well, in these examples, you don't have to take spheres, you can just imagine any kind of shape you like. It is critical that it should be closed, because you should be counting everything that is going in a region. If it is open, some of the electric field lines might just go from the open side and just pass through our surface as it's leaving, so this will not hold anymore. Now let's just make a more precise definition of various concepts over here. The net number of electric field lines. We have to count the electric field lines. Now, how do we count the electric field line, or how can we write it in a form, use some other concept which will be more precise. Now we said that the magnitude of the electric field is proportional to the density of electric field lines. Now we didn't mean, well, we all have a vague idea about what this density is. So if you look at this diagram, the electric field lines of a dipole, you will all agree that the density of the electric field lines in this region is larger than the density in this region. But we didn't really make a precise definition. Now what we mean by a density of the electric field line is the number of lines passing an area A divided by the area. Now, of course, we have to be a bit more careful in choosing this area. That we should choose this area to be perpendicular to the electric field lines. Now, the area A is perpendicular to electric field lines. Now this is how we can define the density. Now let's go back to this diagram. Now we can just imagine such an area over here, which is perpendicular to the electric field lines. Count the number of electric field lines passing through this area, divide by the area, and that gives you the density. Or if you just consider a similar area over here, but of course if we want to consider a similar area over here, we have to be somehow curve it or assume that it is very small such that it is perpendicular everywhere. Now you see that these two areas are more or less equal, but there is one passing through this one and two passing through this one. So the electric field at this point is larger than the electric field over there. Now, but this already gives us an idea of how to count the number of lines passing an area. So the number of lines and area A is proportional to the electric field multiplied by the area. And again, I repeat, this is true if the electric field is perpendicular to the area, or if you choose an area that is perpendicular to the electric field. And this is what we call the flux. Now, if the area is not perpendicular to the electric field, flux, which we also show as phi, E times A if the area and the electric field are perpendicular to each other, or you can also say that this is the perpendicular component of the electric field times the area. Now, any questions on the flux? Flux is mainly, if you want to express it in terms of the field lines, using the concept of field lines, the flux is nothing but the number of the field lines passing through the area. Why we take the perpendicular one? Well, if you consider this case, the flux passing through this area and the flux passing through, let's say, this area, they are the same. There's just one electric field line passing through both of these areas, although this one is an area much smaller than the other one. So the flux shouldn't change as we tilt the area. And that is why we look only at the perpendicular components. Now, you can either consider the electric field multiplied by the perpendicular area, or you can say that the area times the component of the electric field perpendicular to that area. So this area is larger than this one, but the component of the electric field perpendicular to this larger area is smaller. So if we just calculate the perpendicular component times the area for both of these areas, you will see that the flux is the same. Now let's do an example. Now we had already studied the infinite planar charge. With surface charge density. Sigma. So this is our infinite area surface charge. We know the electric field. Electric field is always uniform. And the magnitude is sigma over 2 epsilon 0. Now let's just imagine, first of all, this area over here, such that so it is perpendicular to the electric field. One side A, the other side B. So you can ask, what is the flux passing through this one? Well, the area and the electric field line, they are already perpendicular to each other, so we just multiply the electric field by the area. This is the electric field, and the area is A times B. This is the flux passing through that area. Again, take the same planar charge, but this time I will put an area like this. Again, the electric field lines are uniform. Such that this segment over here is A. This angle over here, let's say it is theta. Now, this area, if you would just look at it from this side, straight from the side, this area and that area would just look identical. I mean, this side is longer than A, but the other side is equal to B. So this one over here it looks something like, no, not like this. It looks something like this. This side is B, this side is C. This side over here is A. If we just take the component of this C perpendicular to the electric field, that is A. Now, what is the flux? Now, this time it is not just E times A, because the area is no longer perpendicular to the electric field. So we should take the perpendicular component of the electric field, multiply it by the area. Now the perpendicular component of the electric field, this is my surface, this is my electric field, this is theta. So the perpendicular component, this angle is also theta. The perpendicular component is nothing but E times sine theta. If you just look at it over here, this is a right triangle. this component is this one multiplied by sine of theta. So the flux is E times sine of theta times A times C. E times A times sine theta times C. But if you look at this triangle over there, this is my theta. C times sine theta, oh sorry, this is B, not A, B. My rectangle has sides B and C. Now C is this length. C times sine theta is nothing but A. So the flux of this new area and the flux of the previous area, they are identical. Well, that's kind of expected because if you think of in terms of the field lines, so these are my electric field lines. One of them I just put it like this, but one of them I just tilted, but took a larger area, so that an observer that is looking straight from this side, they will basically see the same area. And hence, since they will basically see the same area, this larger area, and this area, they are just intersecting the same field lines. So that's why the flux should have been equal, and it just turned out to be equal. This one and this one. No. Above. Yeah. This one and this one, this is E times AB. Questions?
Can we also express it as scalar product of the...
We will. Now, one confusing concept at a time. Any questions about this flux? It's a measure of the number of field lines passing through the area. What is?
Scalar, not vector, right?
I will come to scalar products of vectors, but I need one more vector. I have to define one more vector to write this as a scalar product, but before that, I want this concept of the flux to be clear too. Whenever you think of the flux, you can think of counting the number of field lines. Because when we deal with the Gauss law, we want to count the number of field lines passing through a closed surface.
For example, I put here an object and the lines direction and our lines will stop here or will pass around?
Is there a charge over there?
Not charge.
There's no charge, so either they will go around or they will just go through. Other questions? So let's review the scalar product. Do you remember what the scalar product is? Now we have, if you take two vectors A and B, this is their scalar product. It is a number, and it's just the product of the magnitude times the cosine of the angle between the two. So if this is our vector A, this is our vector B, A dot B, this is our angle theta, A dot B is the product of the magnitude times the cosine of the angle between the two. Now we can also look at it in another form. This side over here is nothing but A cosine theta. Here I have this right angle. So let us just denote it by a parallel, meaning that it is parallel to the other vector. So this is equal to B times a parallel. And similarly, you can just draw a perpendicular line from B to A. This length will be B cosine theta. And if we denote it by B parallel, this is A times B parallel. So scalar product, in a sense, gives you the component of a vector parallel to another vector. So that this is what these parallel signs mean. Now we have defined the phi E to be E perpendicular times A. So this is perpendicular to the area that we are considering. So I will define a vector. No, not E. A, such that A is perpendicular to the area and has magnitude equal to the area. So for example, if you consider this object, here I have an area, a flat area. So I can define this area vector corresponding to this area to be this vector, pointing straight towards you. Or I can also define it in the other direction because it's also perpendicular. This vector is also perpendicular to my area. And I can just choose it to have the same magnitude as the area over here. So that gives me two choices. For a given geometrical area, I have two choices for defining this area vector. So which one to choose? Well, it's up to you. You just define. You just choose whichever one you like. But if you go back to our example of counting the number of field lines, remember there also we said that we will count the number of field lines going from inside to outside as 1, and the number of field lines going from outside to inside as -1. But how do you know the outside and inside? It's just a definition. I mean, usually, if you take such a sphere, for example, you are dividing the universe into two parts. The smaller part you call the inside, the larger part you call the outside, but you don't have to make this choice. That choice of defining the inside and outside is actually this choice in defining the direction of this area. So it's up to you, whichever one you want. So for example, if we have this area, you can choose this as your area vector. If you choose this as your area vector, this electric field line would give you +1 contribution to flux. It is going in the direction of your area vector. And this one would be a -1 contribution. So the choice of this direction, this vector also allows you to take into account the direction that the electric field line goes through. Whether it goes in the direction of A or in the opposite direction, it will contribute differently. Now, let's see. Let's say this is the area, the electric field, at the position of this area. And this is the angle theta. Then we know that the flux, we had defined it as the perpendicular component of the area times the area itself. But the perpendicular component is nothing but the electric field times cosine theta times the area. But this is nothing but the definition of the scalar product. So this is nothing but E dot A. Again, one thing that you should keep in mind, the area vector is perpendicular to the area. So if you make such a definition, this is the flux that goes through an area. Now, of course, here we are always considering the flat surfaces as our areas. Now, in general, the surfaces will not be flat. So this is not a flat surface. So you cannot define a single area vector for this surface. At every point, you have to take a very small area element. That very small piece is flat. If for that very small piece, you define an area vector. And you can consider the flux going through such a curved surface also, by just dividing it into very small, almost flat area elements. Just like when we were considering the ring, we were dividing the ring into very small parts. We can also do the same thing for areas. We divide the areas into very, very small parts. Very, very small areas are almost flat. They will be flat. If they are flat, you can define an area for that very, very small area element. You can calculate the flux passing through that very, very small element. If you sum them all up, that gives you the total flux. Now, take your time to think over this a bit. So we have quite new concepts. We have the concept of flux, which in itself is a bit confusing. But the flux is, in a sense, basically the number of electric field lines. Or you can just say, okay, the flux is nothing but electric field times the area, the perpendicular component of the electric field and the area. Then to write this in a more mathematical formal way, what we do is we just invent this area vector. That is our invention. And you see, if you want to define an area a vector, you have to specify its direction and its magnitude. If you have an area, you already have a magnitude. The only thing left is to choose a direction for that. And if you have an area, the direction is also kind of natural. There's only two perpendicular directions to the area, or just one line, either in one direction or the other direction. So that also specifies a direction to your vector. You have this choice. If you have this area over here, you can choose the area vector to be pointing like this or pointing like this. It's your freedom. Once you choose an area vector, once you choose a direction, you already know the magnitude, so you know the area vector. And once you have the area vector, you can just write the flux in vectorial form. The nice thing about the writing expressions in vectorial form is that they will be, for example, independent of your rotations. If you rotate your coordinate system, this doesn't change. That's one of the main reasons why we want to use vector notation. The area vector is perpendicular to the area. It is defined as perpendicular to the area. That is our definition. Questions? Let's do an example. Let's consider a point charge and consider a sphere around it with the point charge at the center. We already know the electric field. Now the electric field is always radially outward. So it is always perpendicular to the surface. Okay, this is an example where you cannot really talk about a single electric field line, but what you should do is just divide your surface into very small segments. Etc. Now you have to choose a perpendicular direction. The easiest would be to choose outside. So for this area element, this is my area vector. Let me just call it dA. Now the flux passing through that area is the electric field at that point multiplied by dA. But dA is perpendicular to this area. Electric field is also perpendicular to that area. So they are basically pointing in the same direction. E and dA, they are pointing in the same direction. So the scalar product is nothing but the product of their magnitudes. There is no cosine. The angle between them is 0, so cosine of 0 is 1. Cosine of 0. This is E. Well, what is the electric field on that area? The magnitude of the electric field. The sphere has a radius, let's say R. One over 4 pi epsilon 0. Q over R squared. This is the magnitude. This is the E appearing over there times dA. Now let's calculate the total flux. Well, the total flux will be nothing but the sum of the flux passing through all of these very small areas. Now I'm just summing over all these very small patches. This will be equal to sum over 1 over 4 pi epsilon 0 Q over R squared times dA. This is just a constant. It doesn't depend on which patch we are in, so we can just take it out of the summation side. Q is just a constant. Q is the charge over here. All the patches are at the same distance from the charge. So R is the same for all of these patches. So I can just take all of these out. This is equal to Q over 4 pi epsilon 0 R squared sum over dA. Now we can either say that, okay, you will eventually take the limit that dA goes to 0, so you have infinitely many patches, that you have infinitely many terms in this sum, each one contributing a 0, but that is nothing but an integral over the area. But another way of looking at it is you are just summing over the areas of each one of those patches, but if you just sum all the areas of the patches, you just obtain the area of a sphere. And the area of a sphere is what is the area of the sphere? Area. 4 pi R squared. These cancel. Q over epsilon 0. Well, let's go back. You see, here we were actually counting the number of field lines. And we took a very small sphere. If we counted the number of field lines, that is 8. If we took a larger sphere, the number of field lines is still 8. Now, the reason why it's independent of R squared is, in fact, right, this last step. On one hand, the electric field line goes as 1 over R squared. On the other hand, the area increases as R squared. So if you have a larger sphere, of course you are integrating a smaller electric field, but your area is large. E gets small, A gets large. So for the 1 over r squared law, they just cancel. Well, this is a simple example in which we also assume that this plus q charge is at the center. If the plus q charge is not at the center, the result is still the same. If you don't take a sphere but an arbitrary shape, the result is still the same. So you put this plus q charge over here, let's say, and you imagine such a surface, of course a closed surface. Phi E, which we define as E dot dA. This just means that you have this surface divided into very small segments, sum all those segments, sum E dot dA for all those segments. This is what that notation means. And this circle just means that it is a closed surface. This is equal to Q over epsilon 0. It will always be Q over epsilon 0.
Peki şeklin hocam konvex konkav olmasına göre değişir mi?
No.
Mesela arada çünkü bir boşluk var mesela.
Sure. So let's draw the electric field lines. And remember, we have our convention that we will be drawing 8 electric field lines. 1. No, sorry, that's 2. 4. 6. 8. They are all going out. Let's count them. Now this contributes plus 1. This is plus 1. This is plus 1. This is plus 1 because they are all going out. That was our choice. We chose that the outward was plus 1. Now this is minus 1. Now this is plus 1. This is minus 1. Here we have plus 1. Here we have plus 1. Here minus 1. Here plus 1. Here we have plus 1. Here we have plus 1. Well, you see it just goes out, comes back in, goes out. But for this line, the total contribution is plus 1, minus 1, 0, plus 1, plus 1. For this line, we have a contribution of 1. For this line, we again have a contribution of 1. We have 2 plus 1s, 1 minus 1s. So the total number of electric field lines passing through this surface is again 8. That was our convention. That corresponds to Q. It's independent of the shape.
If there was a second charge, change this.
Well, let's see. Well, we already have that graph. You see, we have 2 charges. One charge, the other charge. Now, of course, the electric field line will not be just radially outward, but whatever surface, closed surface you take around this one, which doesn't contain this one, the number of electric field lines passing through it is still 8.
As much as the area
Is closed and contains Q. Now we will generalize this. I mean, for the time being, we have this result for a point charge Q. For a spheral, we will generalize it. And we will say that it is for an arbitrary charge, arbitrary surface, and the Q over here is the total charge inside. But that we will do next week. Let's do one more example. Yes?
I think I just need to clarify if you made a mistake writing a type. You made a typo on the right. No, one little one. Is that please? when you first said summation all the integrals, all the five, shouldn't that be D?
True. I'm summing over these ones.
Isn't the area related to the radius? Can we take radius out of the
Which one?
dA is 8 pi dr, 8 pi I dr.
dA is not related with dr. Not for this surface. Okay, let's give a break now. We will continue next hour.